that bullshit we were talking about, JavaScript. Um, so yeah, I don't know if it was just pure coincidence that this talk is following that one, but there should be some interesting parallels. Um, so I should get this out of the way at first. I don't hate JavaScript. I happen to like it quite a bit, um, but I try to be pretty clear-eyed about it. I miss integers too. Um, so yeah, I want to talk about a similar theme. Oh, you know what? I also wanted to hook up the sound. Where's? Here we go. Okay, is that coming through? All right. So I want to talk about this idea of JavaScript as a virtual machine, and you'll see, I think, kind of what I mean. So yeah, up front, I work for Mozilla. So I don't think of what we do as backroom deals, although I'll admit, yes, there are a lot of players involved in the standards process. So I work for a sort of new part of Mozilla called Mozilla Research, where we do a lot of experiments, a lot of sort of trying out ideas for what we'd like to think is coming up further down the road in web standards. So a lot of this is not stuff that's working today or stuff that's fully working today. It's more like stuff that I'm thinking about, that the people that I'm working with are thinking about, and the stuff that the standards groups that I work with, particularly TC39, which is the standards group that standardizes JavaScript. So this will be a combination of standards work in process and sort of technology experiments we're doing at Mozilla Research. So everybody's kind of into this build step thing these days, right? Zed was just talking about that. Hardly anybody writes production code without there being some sort of a build step in the process. So there was a nice blog post from Rebecca Murphy, who's well known from the jQuery podcast, from her work on Dojo. This came out maybe a month ago. She wrote, "Something has changed in the last couple of years," and she started talking about the baseline of what developers have to, the tools that developers have to know about to build production code. And I think this has been building up actually over a long time. I mean, it really kind of started back a long time ago with things like minifiers and packers, where people were already building their code for the web, a decade ago. But it was maybe just a couple little tools like that, like JSmin. Looks like we still don't have full screen. Oh, well. With lint tools like JSLint and JSHint. But these days we're seeing a lot more build tools. People are working around the fact that, they don't have components, they don't have variables in CSS. They're being forced to write these vendor prefixes, which means suddenly you have to write 5 or 6 times the amount of code that you had to write before. So this build step became kind of a more necessary part of the process. And I think all of that kind of came together and made the world ready for something like CoffeeScript, where really, I like to imagine if CoffeeScript came out 7 or 8 years ago, I don't think it'd be taken very seriously, because really, by and large, it's a convenience. It's like, it's a little nicer than JavaScript, but their whole tagline is, it's just JavaScript. So why would you really buy into having this whole separate tool in your tool chain just for something that's a little nicer? But I think what happened was people already had this build step in their process, so plugging in one more piece wasn't that hard. So why not throw in CoffeeScript and make JavaScript at least a little more pleasant to look at? So Zed's right. People are compiling to JavaScript like crazy. There's this altjs.org, which has a list of languages that compile to JavaScript. And there's all sorts of different reasons you might do that. Maybe you hate JavaScript, or maybe there's just a computational model that JavaScript doesn't provide you that you really need. So I think it really runs the gamut. You've got CoffeeScript, which is really about aesthetics and some sort of small-scale conveniences that when you scale them up, they actually start to add up. Then you've got sort of more grandiose languages like ClojureScript, where they're actually trying a very different programming model instead of the JavaScript programming model. And you get things like macros, which you just don't have in JavaScript. They can also sort of smooth over the lumps in the platform. So In ClojureScript, you get this kind of uniform abstraction for all kinds of data, including the DOM. And the DOM sort of is legendary for how poorly it fits with JavaScript's data types. You've got new experiments like Roy, which is a language that's more like functional programming, statically typed functional programming. So they have things like static types, disjoint unions, pattern matching, really different stuff from JavaScript. You got people who are doing security. So, all those languages like AdSafe or Caja or Microsoft's Web Sandbox. For people who like coroutines, there's projects like Tame.js, which gives you sort of synchronous style programming that's still non-blocking. This is just a short list. There's lots of reasons why people compile to JavaScript. So Zed mentioned this idea of JavaScript as the assembly language of the web, and that's a meme that's been going around for a while. There was a nice blog post by Scott Hanselman from Microsoft on this idea, and he interviewed a few sort of famous people, including several that I work with, and asked what they thought of this. And really the question that everyone asks, you heard this already, is why couldn't we just have a bytecode VM? Why do we have to use JavaScript? Why can't we use whatever language we want and have a nice, simple target language that compilers can target? So it sounds deceptively sort of common sense. Why not have a separate bytecode VM? We actually tried that once. Okay, that's a little unfair, but really, so in that blog post by Scott Hanselman, he interviewed Doug Crockford, and I thought Doug had an interesting point. It's not 100% accurate, but there's something to it. He says, we had always thought that Java's JVM would be the VM of the web, but it turns out that it's JavaScript. JavaScript's parser does a more efficient job than the JVM's bytecode verifier. So what's he talking about there? He's talking about the fact that bytecode languages are often low enough level that there are certain things that you can write programs that really shouldn't be run. They do things that can kind of make the language go insane, particularly if those languages started out with a static type system. So Java's approach, this is the reason why I think this is not 100% accurate, is that Java's approach was sort of built around the Java type system. And you don't have to build a programming language for the web around a type system like Java's. If you look at a language like ActionScript, they had a verifier that's a little lazier. So it's kind of messier. But ultimately, JavaScript's dynamic typing actually works pretty well to replace a verifier. With JavaScript, you load in the code, there's no verification you have to do at all. You just parse it and run it. So dynamic typing actually works pretty well for a mobile code system like the web. You don't need to verify JavaScript code. You just parse it and it's ready to go. Now, of course, now you've lost all of that nice static type information that you'd like for optimization. But modern JavaScript engines like the one like V8, as Slava was talking about yesterday, those can do all sorts of sort of type reconstruction at runtime. They can do optimizations that recover that information. So the name of the game with mobile code is latency. It's all about, can we get up and running as fast as possible, and then can we optimize as we go and mask that optimization. So actually shipping code as source sort of just sidesteps the whole verification question. Then there's the question of bytecode as a transport format. Well, bytecode tends to be pretty low level, and that can actually lead to code bloat. So this is not proof that bytecode is necessarily a poor transport format, but it's not immediately obvious that it is a better transport format. So on top of all of those limitations of bytecode, you've got the problem of trying to standardize a whole new language. If you've ever been involved in the standardization process, starting from scratch is maybe a pleasant thought in the abstract, but in reality, it's not a lot of fun. View source, it's a mix. View source of minified JavaScript obviously doesn't work that great, but still having source as the default format means that there's a large portion of the web that is automatically open source. And I think sort of in relative terms, if we start shipping a binary transport format, you're going to have a lot less of the web being view sourceable. On top of all of that, JavaScript is not only written by compilers. There's still a lot of you out there who are writing JavaScript code and who actually like writing JavaScript code. So my preferred view is that JavaScript actually works well both as a language for humans to write and as a language for compilers to write, for computers to write. So I think JavaScript actually makes for a not unreasonable bytecode language of its own, or a virtual machine of its own. So in fact, TC39 has taken this to heart in our work on ECMAScript edition 6. You can actually see on our wiki the goals that we laid out for edition 6 were to make a better language for applications, because at the time that ES3 came out, and even ES5, the level of scale and complexity of applications wasn't what it is today. A better language for libraries to make it easier for people to write, share, and include libraries, but also a better language for code generators. So it's this combination of making JavaScript better for humans and better for computers to write. So one example of the kind of design challenge you have when you're trying to create a language that works for both humans and computers is something like GoTo. So what might GoTo look like in JavaScript? Maybe something like this. Right? We'd have a couple labels like we already have, and then you could go to one of those labels. If you're one of those compiler writers who's actually targeting JavaScript, you look at something like that and you think, oh man, there's a lot I could do with that. That's the kind of thing that a bytecode VM gives you. Sort of almost every bytecode format out there has some sort of jump involved in it. But GoTo, not the world's most popular programming feature anymore for humans. Probably not something that we want to just throw into JavaScript. So actually there's a nice solution for this that works well both as a sort of high-level human programming construct, but actually can work well for code generators too. And that's the idea of proper tail calls. So with proper tail calls, when you return a function call from a function, you actually, it's sort of easiest way to think about it, you pop the stack before you jump into the next function. And that means that you can have any number, an unbounded number of tail calls, and you'll never blow stack. So you can actually implement GoTo in an even more expressive way. It's sort of like GoTo with arguments. So that same code that we had above with sort of an implicit GoTo from L0 to L1 and an explicit GoTo to L0 and an explicit GoTo to L1, we can implement that if we had proper tail calls in JavaScript. If you tried to write this function today, if it loops enough times, you're going to blow stack. If we have proper tail calls, that can actually go on indefinitely. On top of that, this kind of code can be highly optimized so that it's actually running, like this particular example should be able to run exactly as fast as the GoTo example. So that's a kind of example of what I see as our job of trying to make JavaScript accommodate these two different kinds of users. All right, but at the same time, we're in the mobile era. We have these mobile stacks where there's pretty compelling programming models that are being built on, well, in Android's case, Java, but in iOS, you've got Objective-C and you've got sort of native performance out of the box. Can we, with JavaScript, can we actually compete with native? On top of that, you've got a bunch of native code that's already written and just doesn't work on the web. And is there some way that we could actually make the web able to do the same things that these native stacks can do? So virtual machines are all well and good, but we still have to remember there's all this native content out there, and we're still kind of not dealing with it. I don't like to talk too much about other people's work, and I really don't want to say too much about native client, but it's hard not to talk about native client when you're talking about this question of native. And I think native client is, if you're not familiar with it, it's Google's sandboxing tool that lets you actually run native code in the browser. They currently only do this for Chrome extensions and for explicitly installed Chrome Web Store content, I believe. It's really impressive engineering. It's a cool project. they actually do this sort of combination. I think there's a little bit of static analysis, but they also do this sort of sandboxing where they're dynamically protecting every memory access to prevent it from going outside of this memory process, or this process's memory for the native code that they're running. So it makes it, hopefully, if everything's correct, it makes it impossible for that native code to have any exploits in it, for it to get outside of its protected space. It's an impressive project. They're able, on some platforms, to get really impressive speed. It's also certainly driving a lot of competition. But I don't actually see this as a tenable approach for running native code on the web. It's sort of inherently unportable because you're taking compiled code that's actually, x86 code or ARM code. It sort of goes against the whole idea of writing your code for one shared virtual machine platform, one universal platform. It also locks out potential new hardware vendors who want to come to play. It's also defined by a single implementation. So anytime you try to just write some code and then say, this is the spec, you end up with all sorts of problems where you ended up over-specifying, you can't change your mind later. And yeah, it's antithetical to view source. The fact is, JS actually can sandbox pretty well too. So there's this little bit of binary data that snuck in with WebGL, this little tiny typed arrays spec. How many people are familiar with typed arrays? Not too many? So typed arrays are a lot like JavaScript arrays, but they don't have holes. And when you create a typed array, it's only containing binary data. So it's just an array it's basically an array of bytes. And the nice thing about these things is that JavaScript JITs can go to town with these. They can optimize like crazy. So you can actually virtualize C. You can virtualize a native environment by creating a heap. This heap is just one big, huge array buffer. An array buffer is one of these buckets of bytes. And then you can run a C program by just banging on these bytes. That sounds kind of insane, but one of my colleagues, Alon Zakai, built a tool called Emscripten, which takes LLVM bytecode, the stuff that's generated by the LLVM compiler, and actually compiles it to JavaScript. And the virtual machine that you're running, this sort of virtualized C machine, is this one single array buffer. That sounds usually like completely wacko, like just untenable. How could you possibly get acceptable performance in a language like JavaScript trying to virtualize C? But it works surprisingly well. So I want to do one little demo. So this is the Banana Bread game engine, which is written in C++, compiled through Emscripten. And Alon has been working on building out shims for all of the native libraries. It takes a second to start up. So this is running in my browser without any plugins. And this is a C++ program running in JavaScript. Very violent. It's fun working near Alon because like every day he adds a little bit more to these demos. Like one day he came in last week and said, look, arms. I like this part of the demo. I think that's really cool. Watch this. Okay, so that's just a quick demo of running C++ on the web. So I don't deserve any credit for that. That is entirely Alon Zakai. Okay, so you can actually get sort of shockingly good performance out of JavaScript, but there's a really excellent blog post I recommend everybody reads by Slava sometime maybe last year called The Trap of the Performance Sweet Spot. And he said, beware of these arguments that tell you JavaScript can be as fast as C, or can be n times as slow as C, or can be within an order of magnitude of C. Because when you write code that competes with C in JavaScript, what you're really doing is you're writing code as if you were a C programmer in JavaScript. And the code that you're writing looks nothing like ordinary JavaScript code. These optimizing engines optimize for very specific code paths, and they don't come anywhere near the sort of diversity of styles of programming that you might do in JavaScript. And he's absolutely right. So the way I like to put this is there's a difference between performance and predictability of performance. And in fact, on the web, performance has gotten better and predictability of performance has gotten worse. The smarter our JITs get, the smarter the optimizations are, the harder they are to predict. So anybody who spent any time trying to write high-performance JavaScript, I'm sure runs into this, of just trying to figure out what the hell this engine is doing, why it is or isn't optimizing in different cases. But I think the compiler story can come into play again here. You don't necessarily have to throw away JavaScript and have a whole new programming language in order to get predictable performance. One of the things that you can do is you can write a compiler that does understand the performance patterns of optimizing engines and that provides a better performance model to the user. So another one of my colleagues, Michael Bebenita, has just started experimenting in the last few weeks with a language he's calling low-level JavaScript. What he's trying to do is introduce just a few more additional constructs into JavaScript that look familiar. They look a lot like JavaScript, but they also throw in some C-like stuff too. And that compiles to very similar code to the kind of code that mscripten does. So just like mscripten, there's this big heap binary array. And when you write a function like swap here that has types, it's actually allocating things on a stack portion of that heap. And integers are actually allocated as integers in that heap. So they're very, very compact. And the stack is just pushing and popping, so you get a lot of data locality. So you can do stuff that looks familiar from C, and it's totally unsafe in the sense that C is unsafe. You can have, you can spill over into different parts of the heap, but it's all in this virtualized heap. So there's no security problems in the way having native code on the web would have. So this is just a new experiment. It hasn't really, we haven't gotten into serious optimization or anything like that, but the goal here is to find a way that we can sort of extend JavaScript a little bit with a compiler that adds some new constructs that are easier to predict the performance of. So maybe you'll still write the vast majority of your code in JavaScript or in CoffeeScript or whatever your favorite high-level language is, but when you've got that core computational kernel that needs to be super cheap, or you want to avoid GC allocations, and you want everything to just be numbers in this little heap, you can just tack on a little module in this dialect and use that. So what I'm trying to get at here is that JavaScript actually can be a compelling virtual machine. But in order for it to be a virtual machine, it has to have some of the computational features that a compelling virtual machine would have. And there's still more that JavaScript needs. So before you run away screaming, types tends to be a controversial topic. I'm not about to tell you that I think JavaScript needs a static type system. When I talk about static types, or when I talk about any kinds of types, people's first reaction tends to be, oh my God, please no more abstract singleton proxy factory beans and JavaDoc and private. And I'm not talking about that. I'm talking about stuff like these typed arrays that I was just showing you before, where it's not a static type system, it's just the ability to create data structures that actually have some invariance on them. Data structures like a uint32 array, which is one of these typed arrays that you get in WebGL, where you're saying this is an array of 1,024 elements. There are no holes. There are none of these, weird missing elements that actually drop down to the prototype. Every single one of the elements is actually a 32-bit unsigned integer, so the whole thing is densely allocated. And when you write simple code like iterating over one of these arrays, they JIT really well. So WebGL invented these typed arrays because they had pretty much one need in mind, and that was, we're going to write these shaders. These shaders are going to execute on the GPU. The GPU needs binary data. We need some way of efficiently allocating that data in the CPU and copying it to the GPU. That was like their one use case that they were dealing with when they designed typed arrays. And they had a way to make it efficient, and then they just didn't really worry about ergonomics. The fact is, the single most humbling experience of my life was probably spending an entire day trying to get a triangle to draw on the screen with WebGL. WebGL is not the easiest to work with. And these typed arrays don't make it any easier. In particular, you often actually need an array of structs when you're writing even the simplest of programs. And WebGL didn't give you anything like this. They didn't give you just a simple way of saying, hey, I've got a new struct type, and I want to create an array of those structs. Instead, you have to do something like allocate an array up front of bytes, cast it to an integer array. Like, let's say we had a struct of ints and floats. You'd have to cast it to an integer array with one stride and a float array with another stride and keep casting it back and forth. This is like, writing Fortran in JavaScript. So the first thing that I set about doing when I started talking to the WebGL people was, can we make this a little bit easier for dealing with WebGL programs, for dealing with file I/O, network I/O? It should be possible to read a struct, and it shouldn't require, compiling structs in your head. So for ES6, I've been working on a simple struct type definition facility where you can define your own struct types. You can instantiate them. So we create the point type and then we instantiate it. And they act just like JavaScript objects, but just like typed arrays, they're actually constrained to have the type that you set up front. So every instance of struct here must always contain exactly 2 fields in order, X and Y, each of which is a uint32. So they're very efficiently allocated. They can also JIT incredibly well. So yesterday, Slava was talking about this idea of inline caches. So an inline cache is sort of the first basic optimization that every modern JavaScript engine has to have. It says, okay, I've got this dynamically typed code. I'm writing a function. I've got a function. I'm taking in an argument. Now I have to figure out what kind of an argument it is. For each type test that I do, I can actually generate specialized code that says, okay, now I know I'm looking at an instance of point, so I know certain things about point. Well, typed objects, it knows a lot more about. So as it's going through these different type tests and it says, oh, what I'm looking at is one of these typed objects, all of a sudden it knows X is a uint32, Y is a uint32. I can put them into unboxed registers. I can avoid a lot of type tests. So they JIT incredibly well. So on top of being useful for doing binary I/O, on top of being useful for WebGL, I actually think typed objects can serve compilers as well as they can serve humans for doing things like cross-compilation of languages like C#. So there's a project out there by now an ex-Mozillan who's gone off to do some consulting, Kevin Gadd, called JSIL, where he's compiling C# to JavaScript. And he's got some examples like Bytown Lumberjack, which is an XNA app for the Xbox that he's actually cross-compiled for the web. He's got some performance issues. He's actually compiling, not like Emscripten, he's compiling C# objects directly to JavaScript objects, so he doesn't have that sort of low-level heap. Well, if he could compile to these typed objects, that code would actually JIT a whole lot better. So I've been talking with engine implementers at multiple companies, and they all seem to think that they can get some really good performance out of the idea. Another group that we're talking to is a professor at San Francisco State University, Arno Puder, who's been working on this project called XMLVM, which is an unfortunate name. Basically, they have a sort of simple cross-compiling framework. And one of the things that they've managed to do is to cross-compile Android apps to iOS. So this is another one of those crazy stories. In their case, what they're doing is they're sort of simulating the whole JVM, including the garbage collector, in Objective-C running on iOS, and they're able to take the code written once for Android and run it on iOS. So this is an example of a game that they got running. But we're actually talking with them now about having a new backend for HTML5, and we're particularly interested in seeing, hey, could we take Android apps and actually cross-compile them to boot to Gecko, which is Mozilla's new project for a web-based mobile OS. So on top of having sort of more easily jittable and kind of tighter data structures. The other thing that's really missing from JavaScript is parallelism beyond workers, which are really pretty limited. So every machine, even your phones these days, has all this additional compute power just waiting to be used, and JavaScript is by and large ignoring that extra compute power. So there's a couple experiments that we're doing. We've been talking to Intel about an idea they had. Their research group invented this idea called River Trail, where you can actually create an array of data, and if you write sort of simple maps and filters over that data, they can actually ship that off to the GPU. Well, ultimately, they'll be able to ship to the GPU. They're not there yet. But the idea is that they can take sort of simple programming patterns like map and filter and compile those to massively parallel computation, sort of data parallelism. So this is a simple example of taking a bunch of pixel data from a canvas, converting every pixel's color to grayscale, and then mapping that back to a pixel structure so that it can be put back in the canvas. That is the kind of program that should be able to be spewed to the GPU and done a whole lot faster than it's done sequentially in the CPU. Another kind of similar project that we've been experimenting with, one of my colleagues, Nico Matsakis, is working on this idea of parallel JavaScript, which is a sort of similar idea. It's more of a fork join pattern. So you can create a bunch of tasks by forking them, and they actually can share data with their parent. So this is something you just can't do with workers. With workers, when you do parallel processes, all they can do is pass messages to each other. Passing messages can be expensive. It's also just really awkward sometimes. Sometimes you want to just say, hey, do some work, do it all at the same time, but they should all be able to read some shared data that I've got. And if they're just reading that data and nobody's modifying it, there's nothing unsafe about that. You don't have to worry about race conditions. So the idea of PJs is allow them to share data in a read-only way so that you can do really simple but expressive parallelism. So again, every one of these features, the goal is to make it something that humans might want to use, but that compilers can make use of too. Okay, so my job is still working on the web platform until that next disruptor comes along and replaces it, until one of you comes up with the next better web. But I think in the meantime, JavaScript actually works pretty well as a virtual machine. And I think that we're just seeing the beginning of what people are going to do with compilers. I think people aren't going to wait for every feature to land in the standards before they can start using it. I think they're going to start building their own compilers. And we're experimenting with some of those things too. And I think one of the things that we can do is help them by adding some of the kind of base level functionality that they need to be able to build the languages that they want. But the net effect is we're trying to grow JavaScript both for people and for compilers. That's all I got. Thanks. What's that? Okay. Yeah, I thought I might run early. Lay it on me.
I kind of want to start with 7, if that's okay.
In the work you're doing with for generators, are you going to make it so the generator can instrument where in the original source file an error was, so that when JavaScript sort of maybe gives you an error like it never does, you can actually find it in the original source?
Yeah. So the tricky thing about sort of, some people call them asynchronous stack traces, which is a little of a misnomer because there is no stack anymore from a previous event turn. The trick about that is not having space leaks because you're storing a bunch of unbounded information. I think it's possible in principle to track that information. But I think if we built that into the language, we would end up basically building in space leaks. So
basically the error handling is going to continue to not be that great.
Yeah.
And second question, have you used Lua?
No, I haven't used Lua.
You should use Lua because everything you say that's bad about bytecodes, they solve.
Sure.
There's tons of time for questions. I'm just going to work my way around. If you have questions, just let me know, and I'll get to you.
Hey, in the struct example you had, What was defining the order of the arguments when you created an instance of the struct?
Yeah, so I was playing a little fast and loose there. Even though the standard of JavaScript does not specify the order of object properties, or the order that foreign basically enumerates, in practice, every browser has to respect insertion order for instance properties. So we're talking about for ES6 actually standardizing that, because that's a de facto standard anyway. Once you do that, you can actually count on having APIs that can take object literals where the order matters, which I think is just a lot prettier than having to pass arrays of arrays. So my hope is that we can have a nice, pretty API like this by standardizing on the order of object literals. The fact is today there's all these frameworks where people take an object literal that represents an options dropdown, and if the browsers didn't respect the order, the options dropdown would just get jumbled. So the web actually relies on that order.
So my question is very simple. There was a slide about native client where you said that the lack of view source is a big disadvantage. So does it mean that mscript encode effectively view source, then I get a pleasantly readable source?
It is true that whenever you're compiling to the web, view source is not as useful, but the argument that I'm trying to make is not that view source is always useful, just that when you create built-in technologies that don't have any way of viewing source, that you bring more people to, basically the relative amount of the web that was view sourceable would go down. And in fact, sometimes you can actually view source on mscripten. But yeah, it's all relative. There's not an absolute there.
What about source map?
Source maps are great.
That can help your case, no?
Say again?
This can help your case because you can see
Yes,
the C++
certainly. So source maps do make it easier to actually view the original source if the people who do the compilation provide a source map. Yeah. And the update on that with Firefox is we've got somebody finishing up source maps now. Should be landing in Nightly in the next couple of months.
Hello. You mentioned that ES6 is going to standardize for-in. Do you think this is going to bubble up to DOM so that we can for-in element or for-in canvas 2D context and get all the method names and property in the same order across browsers?
That's actually a good question. We should talk more about that offline. I think that's not something we've considered, but it's definitely worth talking about.
Any more questions? There's one.
Will you be able to define functions on the struct?
Like on the prototype?
Yeah.
Yeah, absolutely. So they're very much objects. They're just objects that have constraints on their instance properties.
Okay.
Any more? That's one. And another.
You've given a couple of examples here of things you would like to add to JavaScript to and enhance the opportunities for compilation to JavaScript. Is this something that should be removed, you think? That would help either human editors but also for compilers to not have to support a feature?
There's all sorts of things that if we could remove them would make compiler writers' lives easier. The problem is breaking the web. So you remove a feature and existing content ceases to work. So generally speaking, we're constrained by compatibility. Occasionally there's some tiny corner case that we can change. And really the only way to know for sure if it breaks the web is to try it and see if your browser breaks. But there's some nasty sort of game theory here, basically. Whoever is the first browser to break that content gets to be the first browser that loses all those users because they go off and use a browser that's not breaking. So If I could remove one, God. Yeah, probably all the coercions in JavaScript. That's generally my first complaint with JavaScript.
I should probably just read the proposal for struts, but I may as well ask you while you're there. Is the object? Could I add another property to it after I've created it, or will that throw an error? So if I did origin.g or whatever and try to write a value to that, would that throw an error?
So it, well, I don't think it would throw an error. Maybe in strict mode. So actually, we're still discussing, and I'm open to feedback about whether these should be extensible or not. I kind of want to collect feedback both from implementers and from developers because the flexibility of being able to extend these objects could be nice, but that could also affect their optimizability. So there's a trade-off, a potential trade-off there, and I don't know. So we haven't actually made a final decision on that. But if they were not extensible, I believe at least in non-strict mode, it wouldn't throw. It just would, as usual in JavaScript, just silently swallow it. But yeah, I'm definitely open to feedback on that. The other thing I want to mention is about the wiki. I'm going to be doing an overhaul of the wiki. One of the things that's become clear is that people find the TC39 wiki completely impenetrable. So I'm actually doing an overhaul of the whole thing. And hopefully in the next month or so, we'll have a wiki that starts with actually high-level rationale, examples, explanations of the stuff that we're working on. So sort of watch this space. Wiki.ecmascript.org should get cleaned up within the next month or so.
Okay. Still have time for questions.
There's
There's
one
one
way back
in
there.
the back. Oh, great. This room is too crowded.
Wondered what your stance on WebCL is. I see it's useful for a certain subset of the problems where you would want parallel and false
So
computations,
I'm just
but
going
you
to be
obviously
frank.
can't do anything.
I really don't like WebCL. So I have not yet been convinced that we know how to make WebCL safe. I also think that the programming model is yet another one of these, like WebGL, incredibly low level, really hard to use for users. And one of the things that I like about things like Rivertrail is that you get a lot of the performance benefits, but it's still a completely sane programming model. It's just familiar map filter kinds of functions that you already have on arrays. So I'm much more interested in features that can be optimized but still are usable from a development perspective. That said, there's momentum behind WebCL, so it's not clear where that'll end up in the standards. But currently, there's a lot about WebCL that makes me awfully nervous.
Since JS Next has new syntax, so it's going
there
to
you
be.
are. Sorry.
Hello. JS Next is going to use a lot of new syntax,
Uh-huh.
so it has to be opt-in somehow. You have to say this is ES.
No. In fact, so you only really would need opt-in if we were making breaking changes in the sense of existing code that worked would stop working. Then we would absolutely need an opt-in because we'd break the web otherwise. But with new syntax, you don't actually need an opt-in. It's just, if you try to use that new syntax on a browser that doesn't support it, it's not going to work. So the usual complaint about adding new syntax is that, well, we can't use it now because browsers don't support it, and we're not going to be able to use it for several years because we have to wait for all of our users to upgrade their browsers. And again, I think compilers help with that story as well. Google has their tracer compiler, which right now is still in experimental mode, but eventually that they hope to be an actual sort of language level polyfill so that you can write content in ES6 and compile it to browsers that don't support it. But you don't actually need opt-in for that. So for a long time, we were talking about having an opt-in for ES6, and I basically killed that because I think it wasn't going to work. I think people just weren't going to opt in, and it just would add yet one more mode to all of these complexities that exist today with different HTML versions, different quirks modes, strict mode in JavaScript. It would be yet one more mode. and I just didn't think that it was compelling enough to be able to remove a couple of features that if people don't want to use them, they won't use them. So at this point, ES6 will be essentially fully backwards compatible. But if there's new syntax, you can't just use that syntax on an old browser. Does that make sense?
Yes, but I can't use struct in my old browsers. So if I'm already using new syntax, why can't you remove some of the old stuff? I might be slow. I'm sorry. I don't understand why when I'm writing ES next, I use new syntax and it won't run in my old browsers. So why can't you remove some of the really awful parts of JavaScript at the same time?
Because if there's an existing website out there, not your page, but some existing page, if we've removed a feature, it just won't work anymore. We could say that if you're starting to use these new features, those old features disappear. I guess maybe that's what you're saying. I think that's going to end up pretty complicated unless you want the opt-in. But I think an implicit opt-in that says if somewhere in the body of my program I happen to mention some new feature, then switch into a mode that disallows features XYZ, I think that's going to end up getting so complicated so fast that it's going to be a rat's nest.
Like strict mode, you mean?
What's that? Well, strict
Like
mode, already a lot of people don't like strict mode, and strict mode at least has one simple opt-in that you just say use strict. If you then make it implicit based on content somewhere in the middle of your code, it's going to be a mess.
Okay, I'm making a note for Douglas that he doesn't like strict mode. I